Hi guys, this is Mrs. Gastler, and in this video we're going to talk about angular momentum. But before we do that, we kind of need to talk about this thing called rotational kinetic energy because we haven't done that yet. It'll go real fast though, because we are not going to derive the equation for it, but we will talk about where it comes from. And like we've been doing in all of this unit about rotational motion, we're going to connect the linear stuff that we've talked about before, that is a nice review, and the rotational stuff. So we've already talked about linear kinematics and the rotational kinematics. You might remember that it's this one right here, with all that stuff and those rotational kinematic equations that look very similar but with Greek letters. And then we talked about linear forces and how that works with Newton's second law, the first law and the second law and the third law even. They all have a rotational equivalent that tells us how things rotate in the same manner that Newton's first and second, third law told us how things move linearly. And we have this linear motion that sometimes we call translational. For some reason, translational motion and rotational motion. This is another word you might see. And we talked about translational equilibrium and rotational equilibrium. And then we haven't really talked about energy, but there's really only one energy linear rotational equivalent to talk about, and that's the kinetic energy. And that's because kinetic energy has some translational motion to it. So kinetic energy is that K equals 1/2 mv squared. And we talked about the rotational equivalent of mass. So when we have K rotational, which we usually write like this, instead of m, what have we been using in the place of mass? Well, mass resists that translational acceleration. Rotational inertia resists that rotational acceleration. So we put I in there instead. And instead of rotational velocity, we have angular velocity. And so that's it. And then you might remember that work is equal to the change in kinetic energy. Well, if you're doing work to make something rotate, it will be the change in kinetic rotational energy. And so we can do a little bit more with the fun, what do you call it, deriving of equations. You could put in F times D, and then it would be torque times the change in, what do you call that, the theta, the degrees there that you're moving, and then you could come up with some other things there. And instead of work equals, not work, what is it, power equals F times V, it would be power equals torque times that omega. So there's all these rotational equivalents there that we have. So as long as you are good at finding those rotational equivalents, then you can keep on going there. So let's talk about the angular momentum. So linear momentum was P, and we do mass times velocity. Now here's a fun one. This one's going to be great. Angular momentum is an L, capital L. I don't know why. If you find out why, you can tell me. I have no idea why they picked L. L is what they use. Instead of mass, again, we use that rotational inertia. And instead of V, we use that angular velocity, omega, okay? And so this one is easy to see. Now that you're really good at plugging in those rotational equivalents into their right places, then it should be pretty easy, okay? And then just like we did with the force, in mass times acceleration, the net force, that is, okay? And since acceleration is the change in velocity over the change in time, and since you can, there's strange noises happening around me, since you can put the mass and the delta V together on top to get the change in momentum, just like that. So the net force changes the momentum. We can do an identical thing over here. Torque net equals I times alpha. Okay, let's put the alpha here, the I there. But instead of, what do you call that, delta V, we'll do delta omega over delta T. But I delta omega would be delta L over delta T. And so the torque net does the same thing that the F net does. So a net force changes the momentum, a net torque changes the angular momentum, just the same, okay? And so that's just another way to write Newton's second law, okay? So we wrote that before, net force changes momentum. In fact, what we then did was we wrote the delta t on the other side, so delta t times the net force. We called that impulse. So we can do that over here, delta t times the net, oh, that's going to get a little confusing, the net torque. That's an angular impulse. See, there's an angular equivalent of everything, okay? I don't actually know what letter we use. Sometimes I use I over here, but that can get confusing. A lot of times I use J for impulse. But the angular impulse, I don't know if that has a letter. It probably does. I don't know what it is though, okay? But just like over here in linear momentum, we had conservation of linear momentum. We called it conservation of linear momentum. We called it conservation of linear momentum on purpose, even they were like, but there's just conservation of momentum. Conservation of linear momentum said that the initial momentum is equal to the final momentum, or the total remains constant. Well, now we have conservation of angular momentum, and it says, it's CAM. It says that the initial angular momentum has to be the same as the initial final momentum. So the total angular momentum stays the same. This one actually has some great and super fun applications, because over here with linear momentum, it's really hard to change your mass. I mean, I guess you can cut off an arm or throw up or something, and then your mass is different, so your momentum changes, but it is really easy to change your rotational inertia. If you are a single object, you can change how you rotate just by changing where your arms are. And that is something that ice skaters, gymnasts, regular ordinary people can do all the time, just to make how they're rotating different. And so this conservation of angular momentum, is one that people can play with all the time. In fact, we have already played with this one in class, depending on when you're watching the video. Conservation of angular momentum is a lot of fun. This one is applicable with a lot of collisions where objects are running into each other. You might have things rotating and combining their rotation together, but it's more likely that you have an object that is changing how it's oriented, and that's changing how it's rotating, okay? Which is fun. Divers, ice skaters, yeah, loads of fun. Last thing that I wanted to say about conservation of angular momentum was that angular momentum, like torque, has direction. And so you have to think about whether you're rotating clockwise or counterclockwise. Let me make a note here. Has direction. In the calculus-based one, we give the direction something based on the right-hand rule, and so it's following your thumb when you use the right-hand rule. So if it's going counterclockwise, it would be coming out of the page, and if it's going clockwise, it would be going into the page. So does torque. So it would go this way or go that way, kind of like you're screwing it in or unscrewing it. But it does have direction. For AP Physics 1, we really only go with counterclockwise or clockwise, okay? But it's important that you include the direction when you talk about the direction of your angular momentum, because that's how you're going to get the momentum to equal out in the end. If it's all in the same direction or you don't include direction, it's not going to work out, okay? All right, so that's it. When you're solving problems, it works just like the way you did it over here. Back in linear momentum. If you have any questions, let me know. Thanks for watching.